Yes, I'm Richard Hipp. I am the guy who wrote SQLite originally. And so here's the story. The original title of this talk was SQLite is, the SQL engine for the Internet of Things. And that was really popular because it had, the right buzzword, IoT, in it. And so I wrote that talk a long time ago, and I submitted it, and everybody loved it. But and then I was reviewing the slides this morning, and what I realized was that the talk I'd originally planned was just kind of an amplification of the keynote that I did on Tuesday. It just went into more detail. So I pivoted this morning. So I'm going to cover this topic very quickly, but then I'm going to go into a lot of detail about how SQLite is put together, what algorithms it's using, how the query planner works. We're going to deep dive and do some really technical stuff. I hope you like this. I'm looking for feedback, especially y'all who know something about MySQL or Postgres. If you want to say, hey, we do that differently, bring it up, because that's what this session is about. But first, I need to go over the IoT aspect of things, because that's what I promised the conference I would do. So, SQLite is the SQL for the IoT. If you came to the keynote, you already know that SQLite is a small, lightweight, compact, low-dependency SQL database engine that runs as a library. It's built into the application, and it's built into all of your cell phones and all sorts of other gadgets, which is the old-style term for Internet of Things. And so this is something that Baron Schwartz said in his keynote yesterday. He said, you should always move the query to the data rather than moving the data to the query, which makes a lot of sense to me. I'd never heard that. But it occurred to me, that's exactly what I need to be preaching, because you know what? In the Internet, all the data is being collected on these gadgets out on the edge of the Internet, right? And then people tend to ship all the data into the data center where it can be queried on something in the data center. And so they're shipping the data to the query. When, in fact, you could, since you have SQLite out there on the periphery in your phone, ship the query out to the data. Now, of course, there are other reasons for shipping the data into the data center, such as you need to archive it or preserve it for long term, or you need to aggregate it across lots of devices. But this is the concept. And this one idea that Baron said yesterday sort of summarizes the other 50 slides that I had originally prepared for you. Was there a question?
Yeah, since you're embedded in everything, I assume it's a viral license, right?
Yes, the license for SQLite is public domain. So you can do anything you want with it. And most of the people who use it, I don't even know about. So that concludes my original talk. Now we're going to change. Now we're going to pivot, and we're going to talk about SQLite internals. And why do you want to know about this? Why would you even care? I mean, you could just use it. Well, the more you understand how these systems work, the better you're going to be able to use them. And bear in mind that what I'm going to talk about is kind of general, at high level. I'm not going to go into too much detail. I'm going to go into some. But a lot of the principles and ideas I'll talk about apply equally well to whatever client-server database you're using. The point of a database, especially an SQL database, is to save work for you, to make your life easier as an application developer. And if you understand and appreciate how much SQL helps you, you'll better appreciate what it's doing for you. Now, nothing I'm going to cover is required for you to understand SQL or SQLite. This is just supplemental material to help you understand what's going on and to do your job better. Now, nothing is required to be a developer, but everything in these notes is required if you want to be an SQL guru. So pay close attention. All right, first key concept. And speaking to lots and lots of people in lots of different environments, one thing I've seen is there are a lot of developers out there that think that SQL is just a wire protocol for transferring your query from the application to the server. But it's really much more than that. I mean, it's a complete programming language. But it's a very peculiar programming language in that it's declarative rather than procedural. Instead of telling the computer what to do, SQL describes what you want, not how to compute it. you're asking a question, you're just saying, hey, this is the answer I want, and then you toss it over the wall to the server and let the server figure out how to do the computation. So, any relational database system, any SQL database system really consists of two parts. There's a compiler that compiles your program, and then there's a virtual machine that evaluates the program. So, for example, here's a very simple query. Select star from table 1. And, different databases do different things, but this is going to be translated into a program, which is sort of I've written out in sort of pseudocode here. You open the database file containing table 1, you rewind the file to the beginning. While you have not reached the end of the file, you read all the columns out of the current record, you return the columns, advance to the next record, and then after you get to the end, you close the file. So when you write that SQL, it does that program, compiles it, and then runs it. Now that one was pretty simple, and you could probably code that up pretty easily using whatever procedural language you were accustomed to. But when you're doing real SQL, you tend to write queries that are looking more like that. How many lines of Python do you have to write to do that? And how many bugs would be in that? This next query, which is kind of an eye test here, this is actually, I pulled this out of the source code for Firefox. And in Firefox, whenever you press a key in the URL bar, and it gives you a list of suggested URLs, do you know what I'm talking about? Not many Firefox users here. You're all using Chrome, aren't you? Shame on you. Okay, but anyway, it does that, and every time you press a key, it runs this query to figure out what URLs to display for you. That's going to replace a couple thousand lines of Rust or C++. That's the power of SQL, is to take these. The whole point of SQL is to take a few lines of SQL code and to translate it into hundreds or thousands of lines of procedural code. And this is very important because, the number of bugs in a program is roughly proportional to the number of lines in the program. So the longer your program, the more bugs it will have. And so if you can shorten your program by a few thousand lines, that reduces the number of bugs. The other cool thing is that you're not really specifying the algorithm. You're just saying what you want. And the database engine is responsible for coming up with the algorithm. And this is a very powerful concept because you can have an application and it's working really well in the lab and you're supposed to ship it tomorrow and suddenly you find a performance problem. Okay? If you've hand-coded your algorithms, you've got to go back and rework, you're going to miss your deadline. But if the algorithm is in SQL, you could probably fix your performance problem by typing in create index. And you could fix that performance problem without having to recompile. In fact, you could fix the performance problem without having to restart the application. It just starts magically working correctly. It's a very, very powerful concept, which I find a lot of people overlook. Okay, so here's the ins and outs of SQL. You've got an SQL statement. It goes into your system, and then what I call the front half is the compiler. It compiles the SQL into a program. And in SQL world, we call that program a prepared statement. And then we have the back half, which is something that runs the prepared statement. And that gives you the results. That's how SQL works. All of the engines work this way. In SQLite, these are the function calls. Well, the compiler for the program is this thing called, this procedure call called SQLite 3 prepare. And, I had a kind of a goofy interface, so I had to have V2 to kind of fix the goofiness while providing backwards compatibility. That was a long, long time ago. One of the curses of being a really popular software project is that you have to maintain backwards compatibility. And I used to I was merciless with Microsoft, because they tend to do the same sort of thing. But then I find myself in that same position, and I'm more understanding of why that happens. But anyway, the output of prepare v2 is an object, which is an SQLite 3 underscore STMT, which is a prepared statement. And then you take the prepared statement and you run it in the execution engine, which is called SQLite 3 step, and that gives you the results. Now, I'm not real up on how MySQL and Postgres do this, but because it's client-server, I think a lot of this is kind of hidden. You just send it the SQL, and it does the prepared statement internally, runs it, and then discards it. I think, I'm not up on this, somebody correct me, is there a way to get a prepared statement and then use it repeatedly in MySQL?
Yeah.
Well, it's kind of...
You say prepare, and then you say execute. You give it a name, and then you execute it.
And you can execute it multiple times. Yeah, it's the same thing, except for here we're dealing with a library, and so, it's actually an object that's right there in your program. So what is this prepared statement thing? Well, yeah, and so a lot of times, a lot of programs have something like, we have an API called SQLite 3 exec, and in pseudocode that just prepares, runs the program, and then destroys the prepared statement. So now this prepared statement thing, let me talk just a little bit more about it. In SQLite, the prepared statement is bytecode. In MySQL and Postgres, the prepared statement is actually a tree of objects. And to execute it, you walk the tree. There are database engines where the prepared statement is actually machine code. So like MemSQL, when they're compiling the SQL, they first translate it into C++, and then they invoke LLVM, and that generates a shared library, which then they link into their application, and then they run it that way. So they're running on bare metal. So this is the architecture of SQLite. At the top of the stack, there's a parser. The parser feeds a code generator, which feeds a virtual machine. Under the virtual machine, there's a B-tree engine. If you were, coming from Facebook, you'd probably strip off that part and put in RocksDB or something. And then below the B-tree feeds a pager, and then there's an OS interface. Let me break this down and talk about this in a little bit more detail. The first two layers, the parser and the code generator, that's the compiler. And this is just standard kind of drag and book compiler theory. Well, kind of, except that we're dealing with a declarative language rather than a procedural language. And then the output of that is the prepared statement, and then to run the program, you've got a virtual machine, and the virtual machine talks to your storage engine. Oh, I think that's on the next slide. So these bottom three are your storage engine. Now in SQLite, the storage engine is a simple B-tree. And we've got layers here. So we've got the B-tree storage engine. The pager is what handles atomic power-safe transactions. And then underneath, we've got a pluggable OS interface. And so, it comes with the source tree has OS interfaces for POSIX and for Windows and for QNX. We used to have one for OS2, but nobody uses that one anymore, so we stopped it. But you can create your own, even at runtime, and plug them in. It's just an object. So that's kind of the portability layer. That's how we're able to run on lots of different platforms. I got a question.
Yeah, I'm not for Facebook. Don't shoot me. So the thing is, can you plug like a different engine in there?
All right, so the question is, can we plug a different engine in there? It's not really designed for that. The interface between the virtual machine and the B-tree is not an API. It changes from release to release, but companies do this. It's happened multiple times. In fact, at Bloomberg, the news agency in New York, all of their content runs through SQLite. But they cut out everything from the B-tree on down, and they've got their own storage engine called ComDB2 that's multi-data center, high availability, highly concurrent, and that's what they use. And so our relationship with them is we just provide them with the parsing, code generating, and virtual machine. And what I've found is amongst people who call themselves database people, especially in academia, they really are kind of interested in that storage engine part. And it was never my career plan to be a database guy. I came into this by accident. My PhD was in artificial intelligence. Okay? And this kind of happened to me back. And so my natural inclination is the code generator, which is the thing that's picking the algorithm to use, which is kind of an AI problem because you're working with incomplete information and trying to come up with the best solution. So I like the top above, whereas most of your hardcore database people really like the part down below. So yes, you can. In fact, also Oracle has taken this stack and they stripped out the B-tree engine, pager, and OS layer and plugged in Berkeley DB. And there have been others that have done the same thing. So not going to say a whole lot about that, but I'm going to talk about the virtual machine, which interested a lot of people that I've talked to this week. It's very simple. There's a big, it's bytecode. It's a 3-address machine. It's implemented, there's a for loop, program counter equals 0, or while program, or for program counter equals 0, while not at the end of the program counter plus, and then inside the for loop there's a switch statement on the opcode. And then we have a lot of cases for that big switch statement, and each one of those implements an opcode. Now, you might be familiar with other kinds of bytecode, like the JVM or for Java or Parrot, and the opcodes there are very low level. It's like move this short integer from that memory location to that memory location, or add 2 integers together, or jump here if that. They're very much like assembly language. Okay, and the bytecode here in SQLite has that sort of thing, but it also has some very high level operations, such as open a cursor on a B tree, seek that cursor to the first row that has a key that's greater than or equal to some value I'm giving you, and things like this. So there's some high-level things as well. In fact, here is an example, and it doesn't line up exactly right. I apologize for that. This is because I'm using LibreOffice. Okay, I apologize. But you can actually, for your homework, what you need to do is go to the SQLite website and download the command line shell for SQLite. It's called SQLite3.exe or just SQLite 3 for POSIX. And it's a standalone executable. Download it and start it up, and it will start up with an in-memory database. And then you can create a table and run this command. And if you put the keyword explain up front, instead of actually running the SQL, it will show you the bytecode that it would have run. And so this is exactly what you see. I'm not going to go through the details of this, because you can kind of see what's going on. There's an opcode. There's 3 integer operands, 32-bit signed integers. There's a 4th operand, which can be, it's a union. It can be a lot of things like a string, a floating point number, etc. And then P5, which is another 16-bit operand. And then the comment field is normally omitted, but if you compile SQLite in a special way, it adds some extra logic to actually put the comments in there, and that makes the bytecode a little bit easier to understand. Now, all of the opcodes are not an API. They will change from one release to the next. I mean, we don't deliberately change them just for the sake of changing them, but every now and then we'll see an enhancement opportunity, and we'll come up with new bytecodes. It's not like Parrot or JVM where the opcodes are predefined and fixed. And you can there's documentation for these opcodes on the website if you want to know more about them, or you can go to the source code. Go to the website, find the source code. The name of the file is vdbe.c, and you'll find this great big switch statement. And before each case, there's a big block comment that describes what that opcode does. And the online documentation for the opcodes is actually generated automatically by scanning the source code, extracting that comment, and reformatting it. So those are the same. And because the documentation is right by the case statement, the idea there is that the documentation and the actual implementation, because they're right beside each other, are likely to agree. And that is true mostly. If you find a discrepancy, please bring it to our attention. We do try to keep them in sync. But, okay, so, one thing that I find, especially with newbies, is that the idea of a bound parameter, and I don't really know how well bound parameters work in Postgres and in MySQL, so help me out here. But in SQLite, anywhere you can put a a literal, you can put like, question mark $1 or $sign, a symbolic name or things like that. And then it generates the bytecode, but then you bind values to that later, and then you can reuse those values. Now, you've got a mechanism like this in MySQL as well, right? So the way, and I'm always getting the question from newbies that say, well, why can't I put a bound parameter for the name of the table I'm querying? Why does it have to be just a substitute for the numeric value? Well, the reason is that bound parameter is really just like a variable. So you can see in this one, it's the same query we had before, but where we're checking for fruit equal to 1, that parameter is right here, this variable. And this opcode is saying take the value of parameter number 1 and store it in register 2. And then it uses that as part of the query. And so then when you bind a value to that parameter in SQLite, it actually goes in and changes the bytecode to actually put the parameter there. So then when you run it, it just uses that value. Okay, so now below the virtual machine, you've got a B tree layer. In the interest of time, I'm not going to go into a lot of detail here because I think most of you guys understand what a B tree is. But the idea is to give you fast lookup, insert, seek, delete, and next and previous. And below that, the pager is what gives us atomic transactions. As far as the B tree is concerned, a database file is just a bunch of uniform sized pages. They're numbered starting with 1. Page 0 is like our null pointer. Whenever you have page number 0, that means that's no such page. So they start with 1, and the pager's job is that the B tree label says, give me page 12, and the pager goes out and finds out where that is on disk, loads it into memory, and returns a pointer to it back to the B tree layer. And the B tree layer says, hey, I want to change page 12. And so the pager then has to make arrangements to make that change atomic and make sure nobody else is changing it at the same time and this sort of thing. So that's the job of the pagers, to take care of transactions. At the bottom layer, we've got the OS interface, which provides portability. It can be changed at runtime. The fact that we can change the OS layer at runtime is critical to our testing regime, because part of the very rigorous testing we do in SQLite is to verify that it responds correctly to obscure operating system errors like disk full and that sort of thing. Got a question? All right, so the question is, backing up, I said I said that the pager made sure that nobody else was changing the page while you were reading it. So, and previously I have said, which is correct, is that SQLite supports simultaneously one writer and multiple readers. So what happens there is that that would be in wall mode. So before it changes the page, before the writer is allowed to change the page, a copy is made, so that the other readers are not confused. So yeah, that was a little bit confusing the way I said that. I was just trying to... okay. All right. Inside the B tree, this is a kind of a logical view of a regular B tree in SQLite. It consists of variable length records. Every record has a 64-bit signed integer row ID. And the records are of arbitrary length. So as far as the B tree is concerned, the records are just a blob. There's no structure to them. We'll talk about how the structure is imposed in a few minutes. But the important point is the records are of arbitrary length. We also use variable length integers in SQLite. So the row IDs are typically small integers, and we don't want to use a full 8 bytes for small row IDs. So we've got a variable length integer format here, so that small row IDs only take 1 or 2 or 3 bytes, and larger ones take more. Now, when I designed this back in 2003, this seemed like a good idea. There are actually much better variable length integer formats, and I rue the day that I picked this one. I should have picked a better one, but that's water under the bridge. For backwards compatibility, this is what we'll live with. The point is that small integers usually take just 1 byte or 2 bytes, and big integers take much more. This is going to be very important in the format later on. So the B-tree structure consists of a root page. I guess this is called B plus trees, where all the data is in the leaves. So there's a root page which contains integer dividers, and that refers to subpages and so forth on down, and that all the content is in the leaves. Now, of course, if there's not much data, the root page is a leaf page, and all the data is in the root page. But as you add more data, it gets deeper, and it keeps splitting. It's the usual B-tree thing. I won't go into a lot of detail here, other than just to point out that it is a B plus tree. Some keys appear multiple times. Non-leaf pages hold only keys. Oh, the fan out is very high. Because these are small integers, 2 or 3 bytes, that are separating it, and then a pointer to subpages, and that pointer is just the page number, which is a positive integer. The fan out here is huge. It can be hundreds or thousands. So even with a table with millions and millions of records, the tree is actually very shallow, and you can get to where you want to be very fast. And all of these B trees, there's one B tree for each table and each index, and they all fit in a single file. And the individual pages can be arranged anywhere in the file. If we know the root page of a B tree, we can follow the pointers to find all the child pages. So all we need to know is the root page. If you want to see how pages are used in an SQLite database, there's a utility program called ShowDB. We don't provide you with a precompiled binary. Grab the tarball, type configure, and make ShowDB, and you'll get this program. And then type ShowDB, the name of the database you want to look at, and page index, and it will give you some output that looks kind of like this. And it will show you for every page in the database file what function or what purpose that page is serving, which is kind of an interesting thing. ShowDB is a very powerful thing if you want to really kind of explore the low-level functioning of an SQLite database. It's fun to play with. The forensic people, because SQLite databases get used a lot in phones, and a whole industry has sprung up around forensic analysis of SQLite databases in phones. And which I'm very thankful that this is an industry that I don't have to participate in, because years ago we used to get phone calls from police agencies around the world. Can you help us? Can you tell us when this guy last accessed the delta.com website or something? And no, we can't do that. I have no idea. But now there's a whole industry that does that, and they leave us alone, which is very nice. Now, so the pages are typically like 4K in size. They can be as large as 64K, but the typical size is 4K. But we can have an arbitrary length data. Remember, SQLite supports text and blobs up to 1 gigabyte. And so not all of the data for a single entry will necessarily fit on a page. And when that happens, you have overflow pages. And here's an example. We've got the row ID at the very beginning, and then the arbitrary content, but it won't all fit. And so in there we put a pointer to an overflow page, and it just forms a linked list of overflow pages. And so I thought this, when I was first designing this file format, I looked around at all the databases I could find to see what the longest blob or string was. And I think the longest blob or string I ever found was like 200 bytes. And I thought, nobody ever puts big data in a database, it was my conclusion. And so I didn't do an elaborate inode thing like in a Unix file system that might have been faster. I just did this simple linked list. And because thinking that nobody's ever going to have like megabyte-sized things, and which is a shame. But it turns out that this is a lot faster than you might think. Even just following the linked list to get to all the data. Now, the fact that it is in a linked list does have consequences. If you're developing with SQLite and you've got big records that aren't going to fit on one page, it behooves you to put the commonly accessed fields at the beginning of the record, because that way SQLite doesn't have to read all the way to the end to get to the data. As soon as it gets to the data it needs, it stops, and it will it won't read the rest. So put your big blobs and your big strings at the end of the table, and put the booleans and the small integers at the beginning, and the frequently accessed stuff at the beginning. Okay, so an index is also a B tree. Every table is a B tree. Every index is a B tree. Indexes are regular B trees where the content... Oh, I've only got 10 minutes left? I need to go a lot faster. I'm so sorry. All these slides are online. Why don't I just skip over the B trees and let's get on down to some interesting things here. The SQLite master table. This is where the schema is stored. This is a regular table. Its root page is always on page 1. And it contains the original text for all the create index and create table and create trigger and create view statements. And that text is in the SQL field. And there's also another field that for each index and table, there's a root page number. So whenever you open an SQLite database, it first just does a full table scan of the SQLite master table, parses all of the, reparses all of the create table statements and builds its own internal symbol table, and then it remembers the root pages for all the tables and indices. And thereafter, whenever you want to try and access an index or a table, you know the root page, and from that you can find all the other pages. So that's how the whole file is put together. There's an example. I'm going to skip over it for time. Let's talk about the record format very quickly. Here's a single record. There's a header. Starts with the size of the header in bytes. These are all variable length integers, and they're usually only 1 byte. See the virtue of having variable length integers? Otherwise, these all have to be 8 bytes each. And then there's these types, and it gives the data type of each column in that record. Now, SQLite is not like other database engines. It's not strict about typing. Some people say that SQLite is weakly typed and the others are strongly typed. I think those are purgative terms. I say that SQLite is flexibly typed, and the other database engines are judgmentally typed. So with SQLite, you can have a column that says a column of type int, and if you try and put a string into it, if the string looks like an integer, it will convert it to an integer, and you're good. But if it doesn't look like an integer, it'll save it as a string or whatever else you did. So we got to save the data type on everything, and the data types are up front, and then the data follows. Here's the secret decoder ring for the data types. So type 0 means it's a null. 1 through 6 are integers of various lengths. 7 is an 8-byte float. 8 and 9 are the constants 0 and 1, and then large things are blobs or strings, and it actually includes the length of the blob or the string. There's an example. The slides are online. In the interest of time, I will not detail the example. The ShowDB program that I told you about before, you can take that and you can use that with a... she's getting ready to hold up 5, I think, I fear. You can use the ShowDB program to actually decode individual records and see how they're put together. This is your homework assignment. Oh, I'm going the wrong way, sorry. So, how much time do I have left, sure enough?
Just over 15 minutes according to the schedule.
15. So the 10 was wrong? Okay. All right. Well, let's talk a little bit about query algorithms then. At a slightly related test. So here is a table, and it's got some fruit and some states where it's grown and the price for each. This is, part of the database for your grocery store. And every entry has a row ID. And I've got, this table has 7 entries. So, but imagine it's 7 million, okay? And this is how it would be represented in memory. The row ID is up front, and then you have the values of each column. And so then, if you wanted to do a query, what's the price of a peach? Of course, one way to do it is to scan every entry, looking for rows where the fruit is equal to peach, and then outputting the price, a full table scan, which works fine when you have 7 entries, but is not the best when you have 7 million. So you could also say, give me the price of the fruit with row ID 4. And in that case, it can do a binary search and very quickly find the index of the row with row ID 4 and give you the price. but that would require all the clerks to remember that the secret code for peach is 4, and that's not good. So we create an index. This is how an index works. An index is just the value of the field being indexed followed by the row ID, and they're in sorted order. So you can see here, we got apple, grape. We got 2 oranges. There's 2 different types of oranges from Florida and from California, but they're also sorted by row ID. So everything's always sorted with an index. And so what happens now is when we ask for the price of peach, it does a binary search on the index to find the first entry where the value is peach. And from that, it pulls out the row ID. And then it does a second binary search to find the row with the corresponding row ID, and it looks up the price. And that is your basic indexed search. I'm going over this really fast under the hopes that you guys have seen a lot of this before. Am I correct in that assumption? Thank you. I'll go fast then. So, and of course, if you're looking for orange, it might pull 2 entries out of the index, look up the row IDs, and go back to those. Now, I think, correct me if I'm wrong, in Postgres and in MySQL, it's not actually row IDs that are looking up, but actually the physical address on the disk. Is that correct?
No, in InnoDB storage engine has the primary key as the...
So in InnoDB does the exact same thing as this. That's good to know. I didn't know that. Postgres, though, actually has the physical address, doesn't it? Yeah. Postgres has the physical address. But same concept. So now we have, what if you say, what's the price of oranges that are grown in California? Well, we could use the same index and look up every entry which has of type of orange, and then check the state. But we had to reject a row. We had to do 3 binary searches in this case. A better approach then, or we could also create a second index on state, but that's the same problem. We could look up all the fruits that were grown in California, but then we'd have to reject grape, and it's still 3 binary searches. So a better approach would be to do a 2-column index, which has both the state and the fruit. And then we do a single binary search on orange in California. We get a single row ID, we look up the value, and we get the answer. Only 2 binary searches to make that happen. Even better is if we put all 3 columns in the index. And then we do a search on orange in California, and we can read the price directly out of the index and never even touch the table. Okay. Confession. 2004, I went to a PHP conference in I think Frankfurt, and I went to a talk with David Axmark, and he was talking about this, and I saw that, wow, that's a really cool idea. I'd never thought of this. And so on the plane ride home on Delta Airlines, I sat there and I typed in support for covering indexes into SQLite. Not making this up. That's a covering index. All right, so we got so what we talked about so far: a full table scan, looking up with one index, looking up with a 2-column index, using a covering index. What if that's an or instead of an and in the where clause? How do we deal with that? Well, we could always do a full table scan. Full table scan always works, if slowly. But a better approach is to use a couple of indexes and then take the union of the row IDs, and then from that union of row IDs, look and pull out the entries from the table. So what SQLite really does is it starts on the top index, gets all the entries there, but it remembers the row IDs it's seen already in a hash table, and then it goes down to the bottom one, and when it's doing the bottom one, if it comes across a duplicate row ID, it just doesn't do that lookup. But that accomplishes the union. Here's something really clever. And Bloomberg told us how to do this. Here we're doing a lookup. Suppose we only have index 4, where the fruit is the second column of the index instead of the first column. And we want to do an indexed lookup on the second column of an index. I don't know what the official name for this is. We call it skip scan. What happens is that we can do an indexed lookup on this. SQLite can do this. It goes down and it says, well, suppose there's a limited number of states. There's really only 50, right? So it takes the first state and says, show me all of the entries for orange in the first state. And then it takes the second state and show me all the entries for orange in the second state. And so forth and so on until it enumerates all the states. And so it's really kind of doing 50 separate queries, one for each state, and then looking for orange. And that way it's able to use an index on this. It's able to use an index for a query where it's only constraining the second column of the index. Now that only works if the first column of the index has low cardinality, if it doesn't have a lot of different values. So, but in a lot of cases, because it surprised you how many people will create an index where the first column of the index is sex or something like that, or or a Boolean, and this is a great way to work around that. For sorting, you can always, if you got an order by clause, you can always run it through a sorter. If SQLite knows to eliminate the order by clause if it's not needed. So you can say order by row ID, and that's kind of a no-op, right? It's just going to do a full table scan. If if you say order by row ID decreasing, it knows how to scan through a table backwards, and it will do that. So the no sort actually happens when you do that. Just because something has an order by clause does not mean it gets sorted. Now, if you've got an index on an object, it will use the index to do the sort for you, if it can. This is still in log in, but it's still advantageous because it uses a lot less memory than a full up sort, and it's especially good if you have a limit, because then you can abandon the sort very quickly. If you had to do the full sort, it would have to scan the entire table, load all of that information into memory, sort it all, and then throw away all but the last two. This one, it just looks up the first two, and it's much, much faster that way. That's the slow way to do it. And of course, if you have a covering index, it just scans right down through there, and that works great. And it knows how to scan them backwards as well. Now, in SQLite, when I originally designed it, I just assumed that everybody would want to use an integer primary key. And that's kind of stupid. But in 2004, it had not yet really gone viral, and I didn't know it would be used in every cell phone in the world, and this was an easy way out. So when you say integer primary key in SQLite, that becomes the row ID. And you have to spell out integer. Int primary key is something different. If you say primary key, any other thing, if you say multi-column primary key, or you say text primary key, what that is really is a unique constraint on the values. There's no difference between unique of something and primary key of something unless that something is an integer. I know that's goofy, I'm sorry. It's just, that's the way it is, and I didn't know that we would be quite this famous. So all of these different ways of creating a primary key on fruit and state mean exactly the same thing. They generate exactly the same bytes on disk. But, it really would be nice to have the ability to have a table that really is keyed by something other than an integer. And so about 3 years ago, we came up with this new type of table called a without row ID table. And a without row ID table is some extra syntax which says, create a table without a row ID, which is to say create a table that is exactly the way tables should be. And this is a new capability. How much time do I have? 5 minutes. Was that why the lights were flashing as a warning? So with a without row ID table, you can get a much more compact representation. You don't necessarily have to have a separate index for the primary key. It's kind of like a clustering index. The indexes on a without row ID table have to include both the columns being indexed and the columns of the primary key, so that it can know how to look up the primary key entry. I know that I'm going through this really fast, and I apologize. Please study the slides separately and send me an email if you have questions. So now you can say, look up the price of the table where the fruit is equal to peach, and it can just very quickly, because it's a primary key, it can do the binary search, find the entry, and give you the price very quickly. The same query using a row ID table would have had to do 2 binary searches instead of just 1. So there can be a significant savings to using a without row ID table. In the interest of time, I'm just going to skip this and go right to the end. People worry, people worry a lot about, how do I make queries efficient? And the thing I always tell people is, don't worry about it. Just write down your queries, and out of a typical application will have 500 separate queries in it, and about 3 or 4 of them might cause performance problems. So first, just write the application. Just write the SQL down so that it works and gets the right answer, and then go back and find the 3 or 4 that might cause performance problems and try and tune them. And the way you do that is to create appropriate indexes. An appropriate index is one where the first columns have very few repeats, have a lot of unique values in them. Run the analyze command, which gathers statistics. In SQLite, we don't gather statistics on indexes unless you're asked to, and that's very important. The next slide will explain why that is. Instrument your code. There are ways in SQLite, I'm not going to go into them in the interest of time, that you can kind of short circuit the query planner and cause it to choose the index that you specifically want. This is all documented online, and I can talk to you about it later. But in an embedded environment like SQLite, it's very important that the query planner be stable. By that I mean you're developing a product, and it's going to go out and you're going to deliver it to millions and millions of people, and you kind of want it to work exactly the same way on your customer's site as it worked in the lab. You don't want everything to be working great in the lab. It goes out to the customer, and suddenly the query planner decides, hey, I'm going to do this query a different way. And usually, it would be right, but maybe it's going to be wrong. So we make this promise with SQLite. If you don't change the schema, and you don't run analyze, and you don't use these special compile time options that we put in there for Bloomberg, and if you don't change SQLite versions, it will always use exactly the same query plan in the field as it's using in the lab, which is a very important thing for the Internet of Things. For something like, for a server-based thing, you want it to be very adaptive and try and come up with the best query plan all the time. But if you're doing millions of these scattered across the world, you want it to be like you tested. Fly what you test what you fly. Yes, sir?
So this is regardless of the table being 7 rows or 700 million rows?
Correct. This doesn't matter how many rows are in the table. Now, if you want to take that into account, and for example, Apple is very interested in taking this into account, there are other provisions. You can force it to consider how many rows are in the table, and for example, by turning on Enable Stat 4. And we've got some new things coming up in subsequent releases that are going to make this better still. There's a new, was that completely out of time that I saw signaled? 1 minute, okay. So, as I said, I put this presentation together like this morning on a pivot, and I kind of underestimated how long it would take. So I apologize for going quickly. The slides will be online. If you can't find them, you can always write to me. I will personally email you the slide deck. We've got time for a few questions if anybody has them. Yes, sir.
So SQLite is supposed to be small and fast.
Yes.
So do you get a lot of pressure to add features that you have to reject in order to...
Right, so the question is, we're supposed to keep SQLite small and fast. Do I get a lot of pressure to take on features? Yeah, I mean, that's the most difficult part of my job, is saying no to people. Or figuring out which features to add and which not to. We've been putting off adding windowing functions for a very long time because yeah, window functions would be great, but they also take up space in the footprint. And so, if you're dealing with a server or client-server database, the extra code for windowing functions is not an issue. That's not the concern. But when you're copying the database library to billions of devices, the extra 5 or 10K to implement windowing functions could be significant. And so, yeah, it's a big problem, and I don't know how to solve it. So, good question. Thank you very much for asking. Any other questions? We're out of time, but I'll still do questions. All right, what was SQLite 4? This is all SQLite 3. SQLite 4 was an experiment. One, it used LSM trees instead of B trees. We did a sensible variable length integer instead of the one that I showed you earlier. We had a pluggable storage engine, so you could... And there were a lot of experiments with this. And some of the experiments worked out really well. We folded them back in. What we found is that LSM trees don't really work well for the workload of SQLite, because with SQLite, you're just doing kind of individual updates. How many transactions do you make against your contacts database on your phone per second? Okay, seriously. And LSM works really good if you're doing lots of transactions, because it buffers them all up, then does the sort in memory, and then pushes them all out to disk linearly. But if you're just doing a single transaction and then doing another transaction next week, LSM is phenomenally bad, okay? but the RocksDB people, they don't understand this, because it would never occur to them that you would have a database that would only have one transaction per week. It's a very different problem. So the LSM didn't really work out for us on that, and it was a lot slower, and so the experiment ended. But we did fold over a lot of the good ideas that we could without breaking backwards compatibility, and that's the story of SQLite 4. Other questions? Back of the room. Do I need to come back there so I can hear you? Okay, the question was, where do we store the temporary tables? If you create temp table, or if I need to manifest a view or something like that.
No, I mean the temporary table you create just before the result.
Yeah, any temporary tables. We create a file in var temp or wherever the temporary space is, and immediately unlink it. Well, actually, you can configure this. That's the default behavior. You can also tell it to just keep the temporary tables in memory. It always keeps the temporary tables in memory until they reach a certain size threshold before it does any I/O. But if the size threshold gets large, or if you tell it, hey, I'm short on memory, it'll push them out to disk. But it's in a temporary place that they're automatically cleaned up if the system crashes.
So it's managed the same way as you manage the main table space, or?
The format of the temporary tables is the same as the main tables. Yes. The way they're represented on disk is the same format, but they're in a different file. They're not in the same file as your main database. Any more questions? Yes, sir. All right, the question is, what is vacuum? Or
Vacuum is possible when the database is on file.
yes, so
If the database is in memory, because I couldn't find a way.
say again?
If the database is in memory,
Yeah, you can vacuum the database anytime you want. Vacuum, as you delete content from an SQLite database, it marks the space that you deleted or freed up as available for reuse, and will reuse it as you need it. But it does not give it back to the operating system. There is an auto vacuum mode that will do that, which causes a lot of fragmentation. And that's a long story. But the point is, you can run the vacuum command. It kind of recreates the entire database and then copies it back into itself, and it smashes it down to its minimum possible size, and erases, and makes sure that all your content has been erased. This is a big problem with a lot of SQLite users, is that if you do a delete from whatever, it doesn't actually overwrite the data. It just marks that area of the disk as available for reuse. And so you can have things that you thought were deleted that are still accessible to forensic analysis. So in Firefox, for example, when you say delete old content, there's a special mode that you can turn on in SQLite that overwrites deleted content with zeros. And it's off by default because that slows things down. It's extra writing, and most people don't want that. But in Firefox, if you want to delete old bookmarks or something, it flips into this secure delete mode and then overwrites it with zeros. But vacuum will also remove all of that old content that would be available to forensic analysis. So, all right, we're way over time. It's been a great conference. Thank you all for coming. Talk to me. Come see me. Thank you so much.